As promised, I'm going to go back to statistical mechanics. If you recall, the whole problem was this. Yesterday we talked about, and in parts today, we talked about reaction pathways. And these are the reactions we have to consider for a combustion chemistry problem. We said that these reactions are more or less coming from our knowledge in thermodynamics. And they are elementary. And it's the many elementary reactions that complete the entire reaction sequence in the overall fuel oxidation process. Okay. The next question we have is, how fast do this reaction process take place? Or what would be the rates of fundamental chemical elementary reactions? What would be their rate constants? And I'm going to talk about the theory governing the rates of chemical reactions here. The origin of the treatment all come from statistical mechanics. So let me go over some of the things I've already talked about 2 days ago pretty quickly, just to refresh your mind. A brief review of statistical mechanics. First of all, in terms of characterizing molecular property. First is degrees of freedom for an Na ion molecule. Having 3 Na degree of freedom, we transform the coordinate such that we attach the coordinate system to the mass center of the molecule. This leads to a new set of degrees of freedom, translational 3, rotational 2 or 3, depending on the molecule is linear or nonlinear, and the remaining is due to vibration. We talked about CO2 molecule undergoing having 4 internal vibrational degree of freedom. We also talk about the water in nonlinear molecule having a total of 3 vibrational degree of freedom. Okay. And we talked about quantum mechanics, where the Schrodinger equation basically comes from and its relationship to classical mechanics. We talked about the Schrodinger equation. We talked about the time-independent Schrodinger equation governing electron interactions. And then this is the part we stopped. One thing I want to fill in here is this whole thing, if you move the wave function out of the bracket, this whole thing inside without a wave function is known as a Hamiltonian. Since we have decoupled the molecular motion into several translational, rotational, vibrational degree of freedom, they are all orthogonal to each other. Then the energy on the right-hand side, that's the eigenvalue, is essentially additive. Okay? If they are additive, then the Hamiltonian must also be able to, you'll be able to decouple them, such that you can write the Hamiltonian for the translational part of partition function operating on the wavelength is equal to the translational energy multiplied by the wave function. Is that clear? All right. Term by term, we derived this equation for particle in a box problem in 1 dimension and in all 3 spatial dimensions. We also derived the equation for energy levels for a harmonic oscillator. We discussed concept of 0-point energy, and we take a real potential energy function, made approximation such that it becomes harmonic and a harmonic oscillator. And with this harmonic oscillator assumption, we're able to label the various vibrational energy levels feasible for a particular harmonic oscillator of a particular strength. We also did something about the rotation. Very quickly, this is the rotational energy. J is the rotational quantum number. B is the rotational constant, which is inversely proportional to moment inertia of the molecule. And we're talking about degeneracy of a 2J plus 1 for each energy level. Okay. One thing that I wanted to just briefly talk about is in spectroscopy, you're going to see many energy units. Those of us who have done mechanical engineering, or you have done mechanical engineering, you more or less are familiar with the unit of a joule. In spectroscopy, many things can be used as energy unit. 1 joule at a more fundamental level is 1 kilogram meter squared per second squared. And the Planck's constant is joule per second. And why it's per joule per second is because the Planck's constant relates the actual energy of a photon with the photon frequency. So it follows that a photon frequency itself can be used as some kind of energy unit, and indeed we do that. Then you have the wavelength, which is the speed of light divided by a photon frequency. That would have the unit of nanometer. You flip this wavelength over. The number you get, though it's not in 1/nanometer, but in wave number, can also be used as energy unit. They're all the same thing. And this is how they are converted from one to another. The reason why I often like to use wave number is because of convenience. Okay? Take, for example, a harmonic oscillator. Carbon-hydrogen bond in any hydrocarbon molecule shall oscillate at a frequency of 3,000 wave number, 3,000 centimeter minus 1. Instead, if you were to express this vibration frequency in 1/2 unit, then it becomes a very big number. You don't like that. We want to express things like 100, like 1,000. It's for convenience. And it's only for that reason all vibration frequency are expressed in wave number. And therefore, the Boltzmann constant and among other constants that has joule in it can be transformed in the wave number unit. And this is the table you can use. Okay. All right, basic statistical mechanics. Well, in thermodynamic world, those properties we learned so far, temperature, pressure, internal energy, enthalpy, and entropy, specific heats, those are called macroscopic properties that you can directly measure. But we know internal energy is a sum of all kinetic energy of the molecule in a diluted gas. All right? But this diluted gas shall have an energy distribution. Not every oxygen molecule in this room fly at the same velocity. Some would fly a little faster, some would fly a little slower. Combining their rotational energy, vibrational energy, there is a spectrum, there is a distribution. The question is, what this distribution is like? And obviously, after you do correct statistics, you take the average. Well, you must reproduce something that we can measure like a temperature. So we know the concept, so to speak, of temperature first before we know the distribution. After all, temperature is directly within our human experience. Something is hot, today is hot, tomorrow is cold. And distribution is something that requires imagination. In a Maxwell-Boltzmann distribution with energy case, it was a back fit to experimental observation. All right? Molecules can be distributed in principle in any way. There is only one, and one distribution will generate macroscopic properties like a pressure, temperature, and internal energy specific heats that are in agreement with our physical observation. That's the goal. All right. So the Maxwell-Boltzmann distribution energy assumes that this is a decay function, exponential decay function, namely, most of the molecules would have the lowest energy possible. And as you move in the energy ladder, the number of those molecules having high energy is fewer and fewer. All right. And in terms of density of energy state, number of energy state between an energy delta, E sub I to EI plus DEI, is postulated to follow this equation. In the denominator is the sum of those things in the numerator, obviously. And it is understood that the bottom part is something called the partition function, as defined. It measures the total number of possible energy states in the molecule. Keep in mind now energy is discretized. Energy is discrete. There are finite level of energy a molecule can assume. A molecule can assume quantum number of 1 million in the translation. vibration quantum number 2, rotation quantum number 3. And added together, it has its total energy. And because the possible energy levels are discrete, the total energy must be discrete too. All right. So we needed to do the statistics for possible energy levels in the molecule. So between quantum world and the classical world, the difference is nothing more but in the classical world, you can think about bookshelves. A bookshelf that has no grid, where books can be slided in anywhere, is the classical world. Quantum world says you have a specific bookshelf for which you can only put book on them, not between them. Okay? Therefore, how you do the combination of the shelves, its height and whatever, is the total number of ways you can put a book into that shelf. That's the statistics we're doing. Clear? All right. So that's what this partition function does. It keeps accounting for the number of ways we can distribute the energy in a molecule. And of course, this is statistics. If I have 5 ways to distribute my translational energy, 10 ways to distribute my rotational energy, then I must have a total of 50 ways, 5 times 10 ways of distributing this energy. In that form, the total molecular partition function is a product of the partition function for each degree of freedom, or each types of degree of freedom. There are 4 parts: translational, rotational, vibrational. There is a little thing called electronic partition function. I'll talk about this a little later. All right. I'll show you why I needed to talk about the partition function shortly. Now, based on that definition, and if the expression for this energy levels are known, like that in the translational energy, you can plug in this E sub j, replacing by the explicit expression for the energy, translation energy level derived from the particle in a box problem. Alrighty? And keep in mind that n is almost continuous. We talk about this problem. Even for a hydrogen atom at a given temperature, room temperature, you will see this quantum number to assume a value that's very large, such that it can be assumed to be continuous rather than discrete. Thus, you can rewrite this sum into an integral. And this integral can be manipulated to show that it has its exact solution. And that's given as this, where V is the system volume. So it says that for translational motion of a molecule in the volume V at temperature T, have certain number of ways how this translational energy can be partitioned. And this is given by this expression. It's related to Boltzmann constant, the mass of that particle, the temperature, and the Planck's constant. All right. Now I'll show you why this equation will quickly give us a basic understanding of what internal energy is. Okay. Then let me define a canonical ensemble. We're not particularly interested at one molecule. We are interested in a thermodynamic system that is composed of n number of molecules occupying volume V at a temperature T. For example, I have 1 mole of gas in 1 cubic centimeter at 298 Kelvin. Thermodynamically, the system is defined because if I take n divided by V, that's the molar concentration. That's a intensive property along with temperature. I have 2 thermodynamic state function such that this system is defined. All right. The NVT ensemble is known as the canonical ensemble. So the canonical ensemble has its own partition function denoted as a capital Q. And the lowercase q derived here is essentially 1 particle when n is equal to 1. in that volume at a temperature T. Okay. Then you ask the question, what is the relationship between the capital Q and the lowercase q? The lowercase q is one molecule describing how many ways you can partition this energy. If I have n number of molecules in the system, the statistics is such that I must have q to the power of n number of possibilities. Does that make sense? It's a statistical statement. Okay? If one molecule have 2 ways to distribute its energy, 2 molecules must have total add together 4. Okay? 3 molecules would have 8, and so on. All right. Then you have to divide it by n factorial to account for the fact that I have just one single component. All the molecules are, in fact, indistinguishable chemically. Therefore, in terms of energy, you have to worry about this thing that is to account for states that are indistinguishable from each other. Now, this might be a little too much for you right now, but in my lecture notes, I've done a coin game. I've done many coin games, flipping coin games in my lecture note. Read it through it if you're interested in exact derivation, and it all become very obvious. Okay. This expression is very tedious to look at it because of n factorial. There's a very useful approximation known as the Stirling approximation. It takes the natural log of n factorial. You can rewrite this into n times log n minus m. Plug this into this equation. You can rewrite this equation here to become that. And you plug in expression for this one molecule partition function, you get this expression. Okay? All right. Now, you ask, what is really the internal energy? If you remember the internal energy by equal partition principle, each degree of freedom is half kT. K is the Boltzmann constant. The total system in 3 dimensions is the 3 over 2 kT per molecule. Where does this thing come from? It comes from here exactly. So the internal energy of a monoatomic gas or contribution of internal energy by a polyatomic gas without considering rotation and vibration is that this internal energy is essentially the mean energy. The mean energy is obtained by taking this density of energy state multiplied by energy level itself. You sum all possible energy level up divided by total number of ways you distribute this energy. This is essentially doing the mean. And you can show this expression may be replaced by this expression given a definition of partition function. And then you have natural log of q, or rather the derivative, partial derivative of natural log of partition function with respect to temperature. Alrighty. You plug the q expression into here. What you realize is natural log of q moving 3 times n over 2 to the front. You have a natural log in front of this whole group. Okay? But this is done with respect to t. So that whole thing goes to 0. What is relevant in this equation is this thing. 3n divided by 2 pulled to the front, natural log of t, take the derivative of that with respect to t, and that's exactly 3 over 2 nkt. N being number of molecules in the system, k being Boltzmann constant, t being temperature. So as you can see, internal energy is basically the mean energy of all molecules, and per molecule divided by n would be 3 over 2 times kT. And you take this now understanding that specific heat is the partial derivative of mu with respect to t, then Cv from the translational part is 3 over 2 times k, or 3 divided by 2 times the gas constant. Indeed, if you look at the specific heat, Cv for argon, helium, those noble gas, they are exactly equal to 1.5 times the gas constant. Alrighty? Of course, if you have diatomic gas, you have to add on top of it rotation and vibration and so on. This is something you've all done in your undergraduate thermodynamics, I hope. The origin of this expression, there's something we actually know very well, comes exactly from the postulate of this distribution function. That's where it's coming from. All All right? Then, let's talk about the pressure. Pressure, by physics definition, Newton mechanics definition, is what? Time rate of change of momentum, correct? And in a gas, this is basically measured as I have a surface. I have molecules in a room constantly striking the surface, many of them. Each time a molecule strikes the surface, got to take it back. I exchange 2 times the momentum of the gas, provided this collision is exactly perpendicular to the surface. And of course, there is, coming in angle, so average out, many times you get a measure of pressure. All right? That's a macroscopic definition for pressure. Can be understood at a molecular level. But the pressure, in fact, has its statistical mechanical meaning. And that statistical mechanical meaning will lead us to understand where the ideal gas law comes from. So ideal gas law is one of this law, in fact, can be derived from more fundamental theory. It came from an empirical correlation for the measurement of pressure, volume, and temperature for a given gas of a certain amount of it. But then later we proved this actually is a consequence of statistical mechanics. So let me start here. You remember that we're talking about a canonical ensemble. Okay, something that has a volume, has a temperature, or a certain amount of substance, known substance, in the volume at a temperature. Within this volume, you have different molecules occupying having different energy level. After all, the Boltzmann energy distribution describes how this energy is partitioned. So let's suppose I can define microscopic energy levels. The first level is called 0. I would find a group of molecules having 0 kinetic energy. They're not moving, except for the 0.8 vibrational energy. I can find one molecule or many molecules having quantum number equal to 1 for one particular translational motion, with the other 2 all equal to 0. This molecule is also not rotating. It's not undergoing oscillation. So on and so forth. You can do this statistical up. But nonetheless, you can always find, for example, an n1 number of molecule having their energy exactly equal to E sub 1. This molecule can be populated in the entire volume. So these are so-called NVE ensemble. Within a canonical ensemble, of course, you can have many of these lowercase NVE ensembles. For that, the energy, there are quite many different energies that you can occupy. There are many shelves on this bookshelf where you can put books. So let's suppose you have N2 number of molecules occupying volume V, all assuming energy equal to E2, and so on. Each of this small box is called a microcanonical ensemble. All right? And of course, if you sum up all the lowercase n, you must recover the total n in a canonical ensemble. All right? Then ask, what is the pressure? Now, keep in mind that molecules having different energies striking this surface would give you different amounts of momentum transfer. So you have to keep accounting for molecules, how many of them, and what will be their energy for each microcanonical ensemble. Well, the way how we do that is we define a component of pressure, and then for an adiabatic isobaric expansion process, from fundamental thermodynamics, we know the work I have done is equal to the internal energy change for that energy level, which is equal to the minus P times dV, and that's the pressure definition, leading to some volume change. And rewriting the pressure in this fashion, then I have partial E, partial V. Now, how much change in energy change in a particular group of molecule with respect to volume. If all of the lowercase n is fixed, if n1 is equal to 1, n2 is equal to 2, and this is not going to change, then total number of n by the summation won't change either. So the lowercase n becomes capital case N. Then the total pressure just simply becomes of the microscopic pressure summed up by the weight by energy distribution. Again, mathematically, from this expression, you'll find that it's exactly equal to this. And with this, you plug in the expression now only the translational part. You will recover it's equal to kT times n over v. Move v onto the left-hand side. What do we have? The ideal gas law. So ideal gas law is a consequence of statistical mechanics. Already? Very good. With statistical mechanics, the only thing that's left is this Maxwell-Boltzmann energy distribution postulate. Nothing else. Everything can be reproduced according to observation. Next question is about what is entropy. Now this thing I've been goofing around, not telling you the entropy story. I've been very vaguely and sloppily telling you entropy is a measure of randomness. And you bought that, that's okay. It's a conceptual understanding. But what is entropy rigorously? What is entropy rigorously is all about now you have a bookshelf. Okay? The more level of shelves you have in this bookshelf, the more ways you can distribute the books you own. Okay? Imagine if you have a bookshelf that has only one shelf. No. You can only put a book on that level. That is associated with one entropy state. You add another shelf. Now, for all the books you have, you can put it on the first level, or you could put a particular book on the second level. There are many ways now to distribute them, right? If you put more and more extrapolate, and you allow each book that can be placed on all shelves available to you, randomness will increase larger and larger. Temperature or energy is nothing more but to say that this bookshelf actually has infinite level. Many of the high level are not accessible to the books. So when temperature goes up, there will be more books that can be populated at a high level. What are the high level? High rotational quantum number, high vibrational quantum number, and so on. That is entropy. Entropy is about how many ways you can distribute molecular energy in 3 modes: translational, rotational, vibrational. Okay. Mathematically, you have a canonical ensemble. The number of ways to place n molecules into the microcanonical ensemble. Each shelf is a microcanonical ensemble. Okay? Each level is a microcanonical ensemble. Is by statistic argument, the total number of molecule factorial divided by the lowercase number in those microcanonical ensemble factorial and a product of them. Again, if you count straight, see where this equation can come from. I've been doing the coin flip in the lecture notes. It's very, very simple, actually, okay, to understand. This equation must be correct. All right, so this is the number of ways how you can distribute a molecule into that many levels of energy. By Stirling approximation, again, it's a mathematical trick. I'm going to expand this to rewrite this equation such that this number of the capital omega can be written as something like that. It can be simplified since Ni over N is basically what? The Boltzmann energy distribution, right? This is number of molecule at a particular energy level I over total number of molecule. That ratio is identical to this equation. Why is it? The argument is very simple. I'm doing 2 types of statistics. The outcome must be equal. One is I'm going to flip a coin 1 million times. I'm going to get 500,000 head, 500,000 tail. Okay? That's this equation. If I take 1 million coin, I flip all of them at once, I end up with exactly 500,000 head, 500,000 tail. That's this equation. They're equal. This and that is equal. All right. When all this is done, then the statistical mechanics definition for entropy is the natural log of that capital omega multiplied by Boltzmann constant. Thus, we relate the number of ways you can distribute energy with entropy. The more ways you can distribute energy, the more random the system becomes. All right. Have you heard about the Shannon law, Shannon entropy? Have you heard about entropy of a CPU operation? Well, computer operation in the most basic form is an entropy operation. And I/O, you do binary operation, the outcome is 0 and 1. 0 or 1, sorry. Before the operation, you don't know whether it's 0 or 1. So you have two possibilities. After operation, you end up with one possibility. It's 0 or 1. Okay? In the process, your entropy drop. Correct? In a CPU operation. And of course, this is not a closed system. You're allowed to see entropy drop. But what is the price you have to pay? You have to put energy into it. So the minimum energy required to do a CPU operation is the Boltzmann constant multiplied by natural log of 2. Where 2 comes from is 2 divided by 1. 2 before operation, 1 after operation. All right? And this thing has a lot of meaning extending into information science, for example. Alrighty? It's the same concept. The remaining is just all algebra and a simple differential calculus. And take this, plug in this whole thing, manipulate it, and what you get is this expression, and entropy at the end is an equation that has 2 terms. The 2 terms is it's related to internal energy. Okay? So as a matter of fact, for a monoatomic gas, you remember the E we derived earlier is 3 over 2 nkt. So the first term is nothing but a constant for an ideal gas, monoatomic. All right? What's important is the second term. Entropy is nothing more but Boltzmann constant times the natural log of the partition function. Partition function measures how many number of ways you can distribute energy, take a natural log of it. The scaling factor always comes from Boltzmann constant is basically entropy. The larger the partition function of a system, the greater the entropy. All right. So, following thermodynamic property now becomes following the partition function. Partition function is what links internal energy, pressure, entropy, and everything else together. It's a number of ways you can distribute energy. All right. I know this thing is, I'm dumping on you a little too fast. Don't worry. If you ever bump into this stuff, go read a little bit of basic statistical mechanics and it'll become all clear. I'll just go through my lecture notes. There I've done more careful derivation of every equation. You'll be able to follow. Okay. The trick is when you learn statistical mechanics, you do some derivation and you look at the physics behind it. All right. Okay, let me extend, generalize. So far we've talked about a monoatomic gas. Polyatomic gas have rotations. They have vibrations. But the remaining problem is all purely mathematical. Mathematical in the sense that you have taking an arbitrary molecule, having rotational degree of freedom, and for one particular rotational degree of freedom, the lowercase 1 molecule partition function is again taking the finite sum. Now I want to do the integral. It's approximation. That approximation a lot worse, a lot less valid than treating the translational part of the partition function. So there's one approximation involved, transforming the sum to integral. The reason I want to do the integral is I have an exact solution out of it. So for a single rotor, the total partition function for a one-molecule system for one particular rotor is kT divided by sigma divided by b. B is the rotational constant, inversely proportional to moment of inertia. Sigma is something we talked about, I believe, on Tuesday or Monday. That's the symmetry number. Again, symmetry number in thermodynamics that impacted entropy, remember, when we talk about this group additivity. There's a little annoying small correction we have to do for entropy. It's a consequence of molecular rotation. If I have a molecule that can be rotated 180 degrees and you cannot distinguish it before and after rotation, the number of ways you can distribute energy goes down by a factor of 2. Is that clear? All right. So that's where the sigma is, okay? And if I generalize to three-dimensional rotor, three independent rotor, you can isolate them by calculating the moment of inertia Ix, Iy, Iz that is rotating about a particular axis by this expression. The key to obtain three decoupled rotor is to define properly the center of mass. All right. These are just a simple algebra that many of you had in junior or sophomore year level dynamics class. And this is, of course, the rotational constant, the b, that can be expressed by as a function of moment of inertia, either x or y or z. Okay. And I won't want to discuss this very much. I just want to bring you some special cases. When you have a molecule that can have three rotational degree of freedom, all assume the same rotational constants, then what you get is this expression. This is all exact integral. If you have a symmetrical top, you have two moments of inertia that are equal, the third being different. Okay? A molecule having certain symmetry often exhibit this type of behavior. This, of course, a spherical top is a total sphere. There's no such thing. Any molecule would look exactly like that. An arbitrary molecule would have three moment of inertia or three rotational constants that are not equal to each other. Then the total partition function, or the number of ways you can distribute the rotational energy, is given by this expression, each contributing kb over t divided by its rotational constant and the square root of it. But this part is all mathematical. Just bear with me. Rotational symmetry number, we talked about this before. That's the sigma, so I'll skip through that. Vibration. The vibrational partition function for a particular harmonic oscillator is plug in the original definition equation for the one molecule partition function. Okay, and it's given by this expression. It can be simplified, this particular sum may be simplified by writing it this way. Again, go to my lecture notes to see the math derivation. At the end, for a molecule having alpha degree of vibration degree of freedom, you have a partition function that looks like that. Don't worry about exact equation. It's not important. I'll show you all this equation when I need to use them. Right. The basic objective we've done so far is, if you recall, we use basic quantum mechanics to derive the possible energy levels for three types of motion in a molecule: the translation, the rotation, the partition, the vibration. Given those possible energy levels, we ask the question that for a given Boltzmann energy distribution, for each degree of freedom, how many ways I can distribute this energy? We relate how many ways you can distribute this energy with entropy. We use the same principle to derive expression for pressure and so on. All right. And the next question is, let me finish the electron partition function and then make a relationship to other thermodynamic properties. All right. The last thing we need to worry about is something called electronic partition function. There are two aspects to this partition function. The first is all molecules electronically have ground state. like a hydrogen atom, its electron likes to stay in the 1s orbital. High electronic state means this electron, by some reason, can be by a photon, being kicked out from the 1s orbital to the 2s orbital. You have to put energy in order to do that. Those are called electronically excited state. The CH star that gave rise to blue color from the flame is because it's electronically excited, having one outer shell electron being excited to the high orbital. This type of high electronic state is not stable. In many cases, the electron prefers to spontaneously jump back down to the low orbital. High orbital, lower orbital is all about how far the electron is to the nucleus. As it jumps back in, it must release a certain amount of energy. That energy is in the form of photon. Okay? Therefore, all molecules, systems, have a ground state, but then must also have some naturally occurring high energy state. It can be very small. The reason they are very small is for any finite value of E2. For example, 5-6 electron volts. It can be shown that by dividing it by kT and then take exponential function of its negative value, the second term, E, the exponential function, in most cases is very, very small. Okay, 1 over 1 million or 1 over 1 billion or whatnot. All right. So this high order term in general can be neglected. That's the first aspect. The second aspect of the problem is there's something called a ground state molecule having some kind of electron degeneracy. The rule is also very simple. For any molecules having no unpaired electron, it's called a singlet. G value is equal to 1. What do I mean? I have two electrons. If all of them are paired up, one up, one down, there's only one possibility you can take. Only one up, one down. If I have a one unpaired electron, my electron degeneracy goes to 2. Because this electron can spin up, it can spin down. Two possibilities. It is said that you have degeneracy, leading to an electronic partition function value equal to 2. Diradicals, you have two unpaired electrons. Okay? You can both spin up, both spin down, one spin up, one spin down. There are, after all, two electrons in two separate orbitals. There are three possibilities. All right. Guess what? Somehow thermodynamic system remembers how electrons spin. How? I do not know. I have not figured this out. The G value in many ways will exhibit, guess what? In many of the chemical reaction rate. And its impact goes into entropy. This effect, just like a rotational symmetry, goes into entropy. Okay. All right. Putting everything together, we're due for perhaps a break very soon. So I hammer you with all these equations. My apologies. It's about done, big equations. There'll be some simple equations coming later. Putting everything together, you have, for a NVT canonical ensemble, the partition function for the system is given by molecular partition function, or one particle partition function, to the power of n divided by n factorial. Plug in the contribution due to translation, rotation, vibration, electronic, you get this equation. You manipulate it, plug in the expression we derived earlier for each of this degree of freedom. Summarize, collect all the terms together. You have, for a monoatomic gas, your partition function would look like this. All right? And this is also in my notes, so don't have to write it down. Based on our discussion earlier, the internal energy may be derived from partition function by taking natural log of this Q, take then the derivative of this long Q with respect to T, multiplied by K, naturally you get this expression. Okay? Therefore, you take a derivative of this U with respect to T, you get a CV. Now, let's look at this equation. It all becomes very clear, and this must be in agreement with your knowledge. For a monoatomic gas, why is this 5/2? Let me go into over here. It's 5/2 for some reason, but I don't remember now. Going back here. This is 3/2. Where did the 5/2 come from? It must be a typo. That's another typo. For monoatomic gas, in fact, this should be 3/2. Okay, my apology. The second, and if it's a monoatomic, all this term should go to 0. There's no vibration or motion. What the heck I'm doing? I copied them. Sorry. I'll correct that. I'm sorry?
CP is CV plus R, right? So you have...
No, CP is CV plus R. So CP is 5/2R. Sorry, this is all wrong, so let's skip. Just you know the mistake. Let's go to this one. Linear polyatomic gas. My apologies. Why don't I see it when I type in the... Yes, please.
On the previous slide, why is there a rotational term for a monoatomic gas?
This should not even be there. For monoatomic gas, guess what? I taught the summer school and taught regular lecture many, many times. And this is at least about 10 times minimum. Till today, I found the typos here. This is so obvious. You're correct. In this thing, let me clear this up, okay? Monoatomic gas should have this term. There's no rotation. It's a dump ball. It's a billiard ball. Also, it has no vibration. This goes away. And for internal energy, this should be 3/2. No vibration. For specific heat, this is 3/2, no vibration. Okay? For entropy, only translational contribution, no rotation, no vibration. There will be a long G exist because of electronic degeneracy. Okay? For a hydrogen atom, it's a monoatomic. Hydrogen atom would have otherwise the same entropy as a helium, except hydrogen atom would have a G value of 2. Not like a helium has a G value of 1, therefore leading to long G1 of 0. My apologies. This is embarrassing, so let me get to the equation that I feel more comfortable with. This is right. For a linear polyatomic gas, the partition function is made up of contribution from translation, rotation, and vibration. No debate. And the internal energy, or rather, if you look at the specific heat, would have contribution of 3/2 due to translation, then 2/2 due to rotation. Okay? You then have the vibrational contribution. Indeed, if you look at nitrogen, if you look at the specific heat, initially it's a constant as a function of temperature. And it's almost equal to 5/2 times R. Until you get to about 700-800 Kelvin, you see this specific heat start to rise as a function of temperature. The reason for that is this last term vibration becomes active. So therefore, this experience essentially, if you look at a specific heat, you can tell that for nitrogen and oxygen like a molecule, at a room temperature, for most of them, that this vibration oscillation, other than a 0-point vibration, is frozen. Only if you heat this molecule up to 700-800 Kelvin, you start to see contribution from the second one. Therefore, the specific heat becomes a function of temperature. I wish I have an example. I will look for an example to show you. And this is equivalent for a story for entropy. This is for nonlinear polyatomic gas, and I won't go through the detail with the exception of one thing. Now, for nonlinear molecule, I have 3 rotational degree of freedom. Therefore, the initial term 3 comes from 3 over 2 due to translation. Then 3 over 2, another 3 over 2 due to 3 rotational degree freedom, each contributing 1/2 times the gas constant. All right? And then you have a higher, you have vibrational contribution in the second term. All right. Once you understand all these sort of things, then you realize that anything about a thermodynamic property is mostly an understanding of molecular parameters. How much does a molecule weigh? That's the mass. And what would be its geometry of the molecule? The geometry gave rise to moment of inertia. Moment of inertia gave rise to the rotational constant. It's all about understanding how atoms interact with each other, for that this interaction gave rise to molecular vibration. Molecular vibration would have their definitive vibration frequency. That goes into this equation as mu is the vibration frequency. I'll make some comments of this frequency when I get back in the last part of today's lecture. With this knowledge, you don't have now to use the empirical group additivity. The question is, where do you get this molecular parameter? The answer is the solution of a Schrodinger equation. So if you, in the future, if you want to invest your time into combustion chemistry, you may have to take a course in quantum chemistry that will allow you to run computer codes like a Gaussian, like a QChem. Those are equivalent of Navier-Stokes equation solver for the Schrodinger equation. Okay? Where's the solution of this equation? You'll be able to determine mu, you'll be able to determine molecular geometry, and hence rotational constant. All right. Now, I did not give you all this equation for nothing. It's not because for entertainment, understanding the physical beauty of how we can derive the ideal gas law from first principles. The reason I want to do that is because I want to say a few things about reaction rate. So when I come back, we will have a fairly lengthy discussion from collision theory, how often molecules collide in the gas phase, to something called a transition state theory, a statistical theory that utilizes the principle we learned in partition function, casting the problem such that we will show even reaction rate may be determined by a knowledge of how atoms in the molecule interact with each other. After all, chemical reaction is just a complex billiard ball game playing on a rugged pool table. And if you understand this potential function, you understand how each atoms on this pool table interact with each other, then you must be able to derive the equation needed to solve for the rate problem. Okay? We'll go back and do one more hour of a little bit more math. I hope that I won't bore you too much with the second part of the lecture. So we take a 15-minute break.